R.D. Sharma Solution Class 12 Chapter 5 Algebra of Matrices Exercise is 5.3. If A is this matrix, prove that A raised n is this matrix for all positive integers n. How do we do this? We will do this and the later 4-5 questions with the principle of mathematical induction. So you need to know mathematical induction before even solving or attempting this question. But I'll give you a hint. I'll give you the steps. How are we going to do this? See, this A raised n is equal to this 1 n 0 1 for all positive integers n. So this is a matrix. So if the first step should be, if it is equal to or it is true for n is equal to 1, then we proceed. So what is a to the power 1? In place of n I am putting 1. 1 1 0 1. See, this is already given. A is 1 1 0 1, and when we placed n as 1, we actually got what is being given. The second one is when, see, we have to assume for n equals k, and if we can prove that if it is true for n equals k, it is also for n equals k plus 1, it is true, then we say it will be true for k, k plus 1, k plus 2, and for all the k's, that is all the n's. So we assume the first step was n equals 1, it should be proven. Then n equals k, we assume it to be true. So we assume it to be. So what we get, we assume that for n equals k, it is given m here in the solution, but you can always use k. So what is a to the power k? This is equal to, in place of n, just put k, 1k 0 1. Okay. And if this n is equal to k, if it is true, and if it is equal to, or it is true for n equals k plus 1, given that n is equal to k, it is true. Then it is true for every n. So what is a to the power k plus 1? How can we write a to the power k plus 1? If I write a to the power m plus n, that is simply meaning a to the power m into a to the power n. So a to the power k plus 1 can be written as a to the power k and a. What is a to the power k? We just wrote it. We also said that it is true. A to the power a raised k is what? 1k 0 1. And what is a? It is already given. It's given already. 1 1 0 1. 1 1 0 1. Now when we multiply this, and if it comes to true for k plus 1, if I do it for k plus 1, what should come? 1 k plus 1, 0 and 1. That is, k should be k plus 1. If it is true for k plus 1, then it is true for every other k or every other n. So let us multiply these two matrices, and the matrices should come as that matrix 1k plus 1 0 1. So let us multiply this row with this column. 1 into 1 is 1, k into 0 is 0, so leave it. 1 into 0, 1 and k and 1 1, 1 into 1 and k into 1, that is this one. 0 into 1 is 0, and 1 into 0 is 0, so 0 plus 0 is 0. 0 into 1 is 0, and 1 into 0 is 1 into 1 is 1, 0 plus 1. So what do you get? Finally, what we get? Let me just change the color now. We get 1 plus k, or I can write it as k plus 1, 0 and 1. So what is this? As I told you, it should come as like this, and for n equals what is true, for n equals k, assumed that it is true, and it is true for n equal k plus 1, assumed n equals k. So by principle of mathematical induction, this is true for every positive integers n. Now this one is also of this type. So if you see the question, the book, what is the question, we need to understand that first. Whether it is b into a raised n minus 1 by a minus 1, or whether it is, which one, you just see. So we'll do it using the principle of mathematical induction. First step, we need to prove it. that this is true for n equals 1. When we put n equals 1, this has to be true. Okay, so this is a raise 1, a raise n is a raise 1, n equals 1. This will be a raise 1, 0, b into a raise n minus 1. Please remember what you see in the question. It seems like it is a raise n minus 1. That is a raised to the power n minus 1. But it is not like that. It is a raised to the power n minus 1 divided by a minus 1. So you will just see. I'll just take care of what exactly is given. And then I'll show you that it is a raised to the power 1 minus 1. And since a raised to the power 1 is a, so a minus 1 divided by a minus 1 gets cancelled. You are going to essentially get b. So a, b, 0, 1. This is what you get, right? So let us see here. So this is like this. A to the power n, b, a to the power n minus 1 by a minus 1. This is like this. And then we have 0, 1. Okay. So this is a raised n minus 1. So a minus 1 by a minus 1. So this gets cancelled. You get b, a minus 1 by a minus 1. It gets cancelled. You get b. Okay. Final is this like this. This is b, a, b, 0, 1. So this is true for n equals 1. And this is the first step in any mathematical induction. It should be true for n equals 1. Now, let us assume, as we did in the previous question, let us assume this is true for n equals k. Okay. So this is a raised k, and we assume it to be true. So this is a raised k, b into a raised k minus 1 divided by a minus 1 and 0, 1. So we assume that this is true, and using this, if we can prove that this is true for n equals k plus 1, this will be true for every positive integer n. Okay. So the final answer will be like this. Let me show you the final answer. What should come? It should come as k should be k plus 1. A raised k plus 1. Then b dot a raised k plus 1 minus 1 divided by a minus 1, 0 and 1. So this is what we should get when we put n equals k plus 1. So a raised k plus 1 can be written as a raised k, this a raised k dot a. Okay. So we'll try to get that what I have written in the purple in the above part. So this is a to the power k into a. So as I said, x to the power a plus b is nothing but x to the power a into x to the power b. So a raised k dot a raised 1. So that is this a raised k. Let me write it here. A k b a k minus 1 by a minus 1 and 0, 1. So this has to be multiplied with this a, b and 0, 1. This multiplication has to be done. Okay. So let us multiply it properly. So this a raised k into a raised k into a raised 1 is a raised k plus 1. This row and this column. Multiplying this b, whatever is with multiplied with b, 0 will be 0. Now this row again with this column. So a raised k into b plus this same thing because it is multiplied by 1. So just write it here. A to the power k minus 1 divided by a minus 1. Now second row with the first column. 0 into a is 0. A 1 into 0 is 0. And b into 0 is 0 and 1 into 1 is 1. Okay. So three things we got. A raised k plus 1 we got. 0 we got. 1 we got. This only the thing which we see, it should come as b a raised k plus 1 minus 1 by a minus 1. This has to come like this. So let us see this. So I am doing it here. The base will be, I am taking the LCM a minus 1. So this will be multiplied a minus a to the power k b into a minus 1 plus b into a raised k minus 1. So this will be, see, I am writing it here, a k b into a minus a raised k dot b plus b a raised k minus b divided by, so b a to the power k and a raised k dot b, this gets cancelled. So this is a raised k b a minus b divided by a minus 1. So what do you get? B. Take b common. What do you get? A raised k into a, and we already know a raised k dot a raised to the power 1 is what? A raised k plus 1 minus 1 by a minus 1. And what was this? This was exactly this one. Okay. So when we did a to the a raised k plus 1, we got this. So when it is true for n equals 1, we prove it for a raised k plus 1. A is given cos theta plus I sin theta cos theta. Then prove by mathematical induction that this a raised n is this for all n belongs to capital N. Right? Okay. So this type of question can come in your exam. This will weight around 5 marks. So a raised n, let us prove it for n equals 1. Because n equals 1 has to be true. So I'm showing it to you here. Just replace n by 1. That is a raised n. I'm replacing n by 1. So a raised to the power 1. So what do you get? Cos into n theta, that is cos theta. N I'm putting as 1. Then I sin 1. So I sin theta. Then we have I sin theta. Then cos theta. So for n equals 1, you got the correct one. Okay. So for n equals 1, you got the correct option. Very good. Now let us assume that this is true for n equals k. For n equals k or n equals m, whichever you want to take, a raised k will be what? So just replace n by k here. This is what we are assuming that it is true. For k it is true. And with this base, we will try to prove that it is true for k plus 1. So cos k theta, I sin k theta, I sin k theta, cos k theta. Just replace n by k. So we are assuming that for any k, that is n equals k, this is true. Now we will check it for n equals k plus 1. So a raised k plus 1. Okay. A raised k plus 1 is a raised to the power k and a raised to the power 1. A raised k we already given here and a is on the top, the first one. So a raised k. So we are multiplying these two actually. Essentially we are multiplying these two. So I am multiplying these two. Cos theta, I sin theta, that is a raised k we have already written, a raised to the power 1 I am writing. Cos theta, I sin theta and cos theta. Okay, so we need to now multiply these two matrices and final answer should give you, wherever k is there, it should give k plus 1. Okay, so I am multiplying it now. See, what should come? As I said, every k should become k plus 1. Then we say that if it is true for n equals k, it should be true for n equals k plus 1. So let us see. So this row with this column, 1 by 1. So I am multiplying cos k theta with cos theta. Cos k theta into cos theta. Plus, now I sin k theta with I sin theta. Now you see, I into I is I square. Because this is complex, so I square will be equal to minus 1, negative 1. So I am replacing this plus with negative sign. Wherever I square will come, it will write this like this. Sin k theta into sin theta, it will be sin k theta into sin theta. This is the first one. Now this row with this column. Cos k theta into I sin theta. Cos k theta into I sin theta. So just write it here. Cos k theta into I sin theta. Plus I sin k theta into cos theta. So this is the second entry. Now we go to the second row. You can take the I common. So I'm taking I common. I'm removing this I, and I'm just making my work easier because I would then have to write all these matrix again. So I'm just taking I common here. Now coming to the second row, multiply with the first column. So I'm taking I outside. I outside. I know I will come outside. Sin k theta into cos theta. Sin k theta into cos theta. And cos k theta into I sin theta. So I is taken already common. So cos k theta into sin theta. This is the first entry. The second one. Now the second row with the second column. I square will be I square, this I into sin k theta into I into sin theta. I square will be minus. So sin k theta into sin theta you can directly write. Then cos k theta and cos theta plus cos k theta into cos theta. Right. Now you see very carefully. We have certain formula, certain identity, certain relationship, trigonometric relationship that we are going to use. Cos A cos B minus sin A sin B. What is cos A cos B minus sin A sin B? It's cos A plus B. Cos A cos B. Let me write it here. Cos A cos B minus A sin B will eventually give you cos A plus B. What is A? K theta. What is B? Theta. So cos K theta plus theta. See, cos K theta plus theta. Okay. Now I am taking common. Cos A sin B plus sin A cos B. So it will be sin A plus B, sin K theta plus theta. Okay. Now this one, again same thing will come. I sin A cos B plus cos A sin B. That is I sin K theta plus theta. This is minus, so cos, you can write it as cos K theta cos theta minus sin K theta sin theta. And it is essentially equal to cos A plus B, that is cos K theta plus theta plus theta. Now, wherever you have K theta plus theta, if you take theta common, you get a K plus 1. You can always write it as K plus 1 theta. So I told you already in the earlier part that wherever K is there, if you can get K plus 1, then it is true for K plus 1. So let us see here. This will be cos, I'm writing K plus 1 theta in place of K theta plus theta. Plus this is I sin K plus 1 theta. Then we have I sin K plus 1 theta cos K plus 1 theta. So is it A raised K plus 1? Yes, it is. It's A raised K plus 1. And that's what we wanted. So we proved it using the mathematical induction. N equals 1, it is true. For K we assumed, and K plus 1 it already came. Same question like this, but I think we'll take it in the next discussion. Thank you so much. Take care of yourself.